So today we discuss the automated aerodynamic shape optimization. We essentially have a closed loop integration of Dakota, FreeCAD and OpenFoam. The executive summary of what we have done, this is a headless loop, so to speak. Goal was to automate the aerodynamic refinement of a mechanical wrench without human intervention, identifying the optimal shape for drag reduction. Now, coming to the stack itself, we had the controller, this is Dakota, running on Windows WSL. The worker was OpenFoam, running on Apple Silicon M4 via multipass VM. The bridge essentially was SSH. We SSH tunneled for file transfer. We achieved convergence in 34 evaluations with 5 major iterations. We corrected the coefficient of drag to approximately 1.12, which matches the standard bluff body physics. And the core insight is optimization relies on relative consistency, not absolute accuracy. So moving from intuition to mathematics itself, design engineering used to be about intuition, guessing what shape works best. Today, we are going to replace guessing with math. Normally, if you want to make a wrench more aerodynamic, you tweak the CAD, export, mesh, run CFD, check the drag, and repeat. It's slow, boring, and you might miss the best design. What we are doing is we are building a robot. We connect the optimizer, Dakota. We connect it with the CAD engine, FreeCAD, and ultimately the combination of two will be closed with the OpenFoam loop. We essentially press go, walk away, and come back to a mathematically optimized shape that minimizes drag automatically. So for us, we have this virtual engineering team essentially. Think of this as a relay race where text files are the baton. These 3 programs don't natively talk to each other. They don't have plugins for one another. We communicate using text files. This becomes the universal language, so to speak. So Dakota writes a text file. This is params.in. The script reads it. FreeCAD makes the STL. In accordance with these parameters, OpenFoam reads the STL made by FreeCAD and ultimately spits out a text result in results.out OUT. Now, Dakota essentially acts as the brain or the conductor, so to speak. It doesn't really know what a wrench is, it just sees numbers. FreeCAD, OpenFoam, these are the workers executing the actual vision. Coming to the architecture itself, we could not run Dakota in the Apple Silicon because of the architecture mismatch. Now, because there is such a mismatch in between here, we would like to, let's say, run part of the solution in Windows and part of the solution in Apple M4. The reason why we chose Apple M4 is because the ARM64 architecture with Apple M4 silicon chip, it's really fast. OpenFoam runs very quickly in this particular architecture. So we essentially did the SSH tunneling for text file transfer. OpenFoam runs, gives out the CD value. Dakota reads the CD value and chooses the next design parameters for FreeCAD to create your STL. And this loop just keeps going on. So in essence, this is the process loop. Dakota, it writes the parameters, params.in. The SSH transfer moves this data to the VM. FreeCAD in your Linux or Mac, this can generate the geometry and ultimately you interface it with OpenFoam to create your mesh. And once the OpenFoam loop is finished in your Mac device, this essentially goes to your extraction for results.out and Dakota reads the result. It will calculate the gradients and ultimately spit out another params.in file so that this loop keeps on going. So I wanted to talk about how does Dakota essentially, calculate for you what it wants. The analogy that I'd like to make here is the navigation of a foggy mountain. Imagine you are blindfolded on a foggy mountain trying to find the lowest valley. How do you move? Well, in Dakota, there is an algorithm here which is called conmin_FRCG. This is the Fletcher-Reeves conjugate gradient method. This is essentially a gradient-based method. So in the analogy of a mountain, your position on the mountain is the design parameters that we are choosing. The elevation itself is the coefficient of drag. So since you do not know because of the fog, you feel the slope under your feet, which is the gradient, to figure out which way is down. So a question arises here, why doesn't the optimizer just make the wrench microscopic? Well, it doesn't do that because we are, setting some boundaries, some bounds. We tell Dakota, hey, the handle must be at least 150 mm long. This forces it to find the best shape that still functions as a wrench. So in a sense, OpenFoam gives us the answer, but not the direction. So essentially we use calculus, we need a derivative or slope to optimize. OpenFoam being a black box, you put your geometry in, you get the drag out. It doesn't tell you that, drag decreases if you make the handle longer. So Dakota runs the base design, then it intentionally runs a slightly wrong design. That is to say, it will add some, 0.01 mm to the length or so on and so forth. Then it will compare the two drag numbers. If drag went down, it knows that longer is equal to better. Now, the cost of running all of this, so for instance, to take one step, we have to run the simulation n+1 times, where n is the number of variables. So the more your number of variables, the more amount of iterations you will be going through. That's a very strict computational cost that you have to bear. So now that we have an idea of how Dakota takes care of optimization from its end, let's talk about the CAD itself. So CAD without a mouse, this is the power of parametric Python scripting. Most people use CAD by clicking buttons, but we can't click buttons 300 times while sleeping. We use FreeCAD as a Python library. Coming to the parametric analysis itself, we don't just scale an STL, which distorts the shape itself. Rather, we rebuild the object from scratch using constructive solid geometry library every single time. This keeps the fillet smooth and holes essentially, round. And there is one more issue with FreeCAD when you get to exporting in the STL format. So this is the millimeter versus meter issue ultimately. So CAD kernels essentially hate tiny numbers because tolerances tend to fail. So CFD solvers, for us at least in OpenFoam, it needs in meters in SI units. So we model in millimeters for stability, but we apply the 0.001 scale only when exporting the STL, because if you make a 200 mm length wrench and export it in STL, it will still see it as 200 units and then translate that to 200 meters. So we would need to essentially fix this particular thing here. So the parameters that we're talking about, the 4 different parameters that we have: the handle length, the handle width, the jaw angle, and the head size itself. As I said before, geometry kernels often fail when handling tiny numbers, but CFD solvers require SI units itself. So when we export it with a scale factor of 0.001. Now coming to how everything integrates from your FreeCAD to your OpenFoam, there is something called bash scripting. This is the unsung hero of automation. This script essentially translates the 3 different languages that we are using. So bash script is the only thing that actually runs. Dakota just calls this particular script. So it uses tools like grep, awk, which essentially try to find certain keywords that we are interested in. So what happens if you want to figure out what is the value of your drag inside your post-processing folder. So grep or awk, these try to pull these numbers out for your Dakota. Similarly, there is error handling as well. So what would happen if FreeCAD creates a broken geometry, or if your mesh essentially explodes? So we have built a safety net. So if OpenFoam crashes, the script returns a penalty value, which is a very huge drag number. This tells Dakota that, hey, don't go that way. It's a dead end, preventing the whole optimization from crashing. So the solver that we're using, this is simpleFoam, because we are very much interested in steady state analysis with RANs. The turbulence model we have used, this is K epsilon, and we are computing in parallel on 4 cores on Apple M4 chip. The meshing, the solving, all are fully scripted within the VM itself. The choice of OpenFoam version, this is OpenFoam v2506. So then comes the concept of the virtual wind tunnel. One of the very initial questions that I keep getting many times is why OpenFoam? Straightforward answer, it's free, it solves the NS equations quite accurately and is fully scriptable. These are things that you should be looking for if you want to create your design optimization loop. If your CFD solver package is not iterable, if you cannot interface with it with text files, it will be very difficult for you to move forward with the design optimization aspect of it. Next, there is the snappyHexMesh. snappyHexMesh is probably the MVP here. We throw new weirdly shaped STLs at it every single iteration, and it automatically wraps a high quality mesh around it where no human cleanup is essentially required. In this instance, we've become quite lucky because the geometry is already made by FreeCAD, and we know there's no cleanup that is required there. So with respect to OpenFoam, we only care about one number here, CD. The script essentially ignores the pretty pictures and hunts for that single value in the text logs. Now coming to what engineering assumptions we have taken, there is the reference area itself. Now there is a very interesting aspect to how an optimizer works, and I wanted to cover that here. So for instance, the length that we are talking about, this is 0.2 meters and there is a width of 0.03 meters. If you take an area reference from this particular aspect, the area reference will be somewhere around 0.006 meters square. Whereas from front, if you want to take a look at that, which is to say from your jaw itself. So if you want to take a look at what our frontal area would be, this is somewhere around 0.00054. So we are off by a factor of at least 10. Now 10 or 11, let's say. So the reference area that I've taken for OpenFoam is the one on top here, the planform area, just to demonstrate that even though you give the wrong area reference, you will still get the right design iterations within your OpenFoam. The reason being, mathematical consistency for optimizer is prioritized over immediate physical readability, which is to say that we measured the mountain using a different ruler, so we just need to scale it appropriately. So while solving for your aerodynamic drag here, we essentially ensure that if our run anywhere fails, we just return a penalty value, which is to say a CD value of 1000. So optimizer will just take a look at it and understand, hey, there's an uphill here, and we'll just move away from there to the another direction. So now that we understand that the script has pulled the wrong reference area, there is one other thing that we've also done. The script pulled only the front value of coefficient of drag. When OpenFoam writes the force coefficient values, it will write it in total coefficient of drag. Then there is the coefficient of drag at front and rear. So total coefficient of drag will be the sum of front plus rear, and we for our analysis have only pulled the CD front. So in this linear flow regime, minimizing the frontal component sort of correlates 1:1 with minimizing total drag. The optimizer still finds the correct value despite partial data. So ultimately, the way in which our algorithm works, this is the gradient-based optimization, Conmin FRCG. First, we introduce perturbations for sensitivity testing, and we calculate the gradients between iterations. And once we realize that we are going, lower and lower into the valley, perhaps we are converging towards the right design. If not, we will still introduce perturbations into our analysis, which is to say we will tweak our parameters or variables slightly to feel the slope of the data, then take a calculated jump downhill towards the optimal design. So this gives rise to a democratized high performance engineering. Essentially, we developed a link where we have efficiency with respect to scientific exploration, which exceeds human intuition. We are working with zero cost, except for hardware. We are 100% free and open, which is open source software. We are also working with modular loops, where the loop of OpenFoam is not exclusive to what we are doing. We could still swap it with SU2 or ANSYS via a driver script. That would become quite easy. And the script that we've developed is also quite scalable. We can connect whatever low computational resources machine you may have to an HPC cluster via MPI or SSH. So finally, talking about the convergence data itself, please remember this is just talking about the CD value of your front. So we started somewhere around 0.1, and as we ran approximately 34 CFT simulations, the final raw objective became 0.0508. The final geometry, which was essentially optimal, is what we have defined. There is the head has added 0.05 mm. There is the jaw, in which we have reduced the jaw angle, the opening angle, and ultimately there are small negligible changes when it compares to the robust baseline itself. So Optimizer created a slight aerodynamic fairing. This is the nose cone to shield the handle from turbulence. That's pretty much what we have done after 34 iterations, which is to say, hey, your initial guess itself was really good, and whatever design we are seeing right now is marginally better than what we could see previously. And again, just to remind, this is just with 4 different variables that we've spoken about before. If we again introduce fillet radius, if we again introduce a few other parameters in here, the aerodynamics of our jaw or aerodynamics of our wrench would change quite vastly. Now, because we have taken the wrong area and we have taken the incorrect value of coefficient of drag, which is to say we have not taken the total coefficient of drag value, we can still derive and correlate here. So the raw optimization output, this is somewhere around 0.05. The correction here is just to double it, because the frontal and rear coefficient of drags are very similar to each other. So the CD value total, we have 0.1016. And second correction we have, this is the area ratio. So the plan form divided by frontal that we saw previously, we get a factor of 11. So if we multiply the coefficient of drag, the partial drag that we have with this particular factor, the final corrected coefficient of drag that we have is 1.12. This is still in the range of a standard bluff body, which is to say that the system is still physically accurate. So ultimately what we see here, the system is fully automated. We have successfully changed geometry using Python. We have introduced the OpenFoam loop, which triggers the machine to adapt automatically. We have ensured flexibility, where we have decoupled the architecture, allowing for swapping of your solvers or any optimization engine itself. And ultimately the core lesson we have, regardless of what value of area or what value of coefficient of drag we were using for our optimizer, it matters more in regards to what consistency you are following when compared to absolute accuracy, because the relative slope matters much more than the absolute elevation. So what we have built here, this is a blueprint for automated discovery. This architecture serves as a foundational template for complex engineering problems. By decoupling the optimizer, the geometry engine, and the physics solver, we create a flexible system capable of solving multi-physics problems beyond simple aerodynamics. So as we come to an end, I would just like to give you, what references I have taken. Essentially, you can take the Dakota, you can take a look at the website, the Sandia National Laboratories Dakota has very good documentation. I would highly urge you check out a few videos on YouTube as well, where people have interfaced OpenFoam with Dakota, and people have also interfaced OpenFoam Dakota with online web browsing CAD software. This is OnShape essentially. With respect to the CFD solver, all the way from version 2306 to 2506, the documentation pretty much remains the same when it comes to how you define your force coefficients, how do you calculate them, and what type of files do you require for setting up the turbulence analysis, so on and so forth. With respect to the geometry generation, you can very easily use FreeCAD because FreeCAD has the Python API. There is a lot of documentation available there as well. Please take a look at there. And coming to the infrastructure, it's imperative if your machine is not powerful enough that you connect to hardware which is much more faster, much more powerful than what you're working with, because what will end up happening is a single aerodynamics analysis of approximately 5,000 iterations. It will end up taking about 10 to 15 minutes depending on the amount of cells that you're working with. So 10 to 15 minutes for a single iteration, and you can just take a look at 34 times that or 50 times that, 100 times that, so on and so forth. And this will very easily ramp up your analysis time, and ultimately you will be just sitting next to your computer and trying to understand, hey, has my optimizer actually optimized my parameters for me or not? So that's pretty much about it. This was an attempt with the first 4 parameters that we spoke about. Perhaps we will run this analysis using other parameters and figure out if we are working with the right ones. So this becomes the first iteration. The values that we got, the 4 parameters, we will use those as our jumping point, and then try to optimize the other parameters as well, giving them the right amount of bounds as well. So let's do that for tomorrow and we'll discuss in detail. So see you tomorrow.